Flip on the light switch. Did the light come on? Of course it did. It seems like magic, but have you ever stopped to think about exactly how the electricity that powers your lights and other appliances is generated? It's a very interesting process that requires magnets and motion. About 200 years ago, an English scientist named Michael Faraday first developed a method of producing electricity that utilizes magnets, a process called electromagnetic induction. Today, we still generate electricity in much the same way. Faraday's law says that the rate of change of the magnetic flux through a conductor will be equal to the induced EMF, and Lenz's law can be used to determine the direction of the induced EMF. Faraday discovered that changing the amount of magnetic field passing through a coil of wire, a quantity called magnetic flux, would induce a current in the wire. So, what exactly is magnetic flux? All magnets create an invisible magnetic field around them, and the amount of this field that passes through the center of a coil of wire is the magnetic flux through the coil. The word flux is derived from a Latin word, meaning flow. So think of magnetic flux as the amount of magnetic field that's flowing through the area formed by the coil of wire, just like water might flow in a pipe. The magnetic flux can change if the magnetic field changes or if the coil rotates, and in both cases, this changing magnetic flux will induce a current in the wire. This equation shows you how to calculate magnetic flux, which is measured in units of Webers, abbreviated WB. A equals area, B equals magnetic field, theta equals angle between A and B. Phi sub m equals BA times cosine of theta. Faraday's law describes the relationship between the potential difference between the ends of the wire, also known as the EMF, which stands for electromotive force, and the rate of change of the magnetic flux through the coil. This induced voltage will cause current to flow in the wire, but remember that this will only happen if there is a change in magnetic flux. It's not enough simply to have a wire in a magnetic field, but the field must be changing in some way. Remember that before you can calculate the induced EMF using Faraday's law, you'll first have to calculate the magnetic flux using our first equation. N equals number of loops. Delta phi sub m equals change in magnetic flux. Delta T equals change in time. Epsilon equals induced voltage, also known as EMF. Epsilon equals negative n delta phi sub m divided by delta T. Faraday's law. How can the magnetic flux change? Well, there are a few ways this could happen. First, you could move the wire. The voltage induced in this case is called Motional EMF because it's caused by moving a wire through a magnetic field. Second, you could make the loop bigger or smaller, and therefore change the area. You could also rotate the loop so that the magnetic field that passes through it changes. This is what happens in an electric generator. Did you notice that there was a negative sign in Faraday's law? You may have wondered what that meant. Initially, in Faraday's original formulation, there was no negative sign. The negative sign tells you what direction EMF will be induced, and therefore